Last objective for us. So this is a huge summary of the graphic organizer stuff. We'll even look at vocab graphic organizer as well. But these are the things we need to be able to do. We need to be able to explain how concepts are similar and different. That's how the graphic organizer, the blue one, is set up. We need to be able to write equations for functions and for working with arithmetic means. And then we need to apply and explain the exponents rules. So I've already put some information here to talk through. We should already have this filled out. But when it comes to arithmetic sequences versus linear functions, similarities. They both have additive rates of change called what? Okay? So it is only called a common difference actually for an arithmetic sequence. So an additive, you can say here the additive rate of change equals a common difference. We'll talk about why that is in a second to explain why. Does anyone know what we call the additive rate of change for a line though?
Slope.
Yes. The additive rate of change is definitely called slope. But again, I want you to notice the focus here is that arithmetic sequences and linear functions have additive rates of change. If you did not already have that note down about how they are similar, you should write that note down. Okay? Now a quick note, and this will come up more heavily when we get to the end of this unit. How do we calculate slope?
Rise over us.
Okay, so y equals mx plus b, that's the equation of one of the equations of a line. But I meant to start off with what symbol or what letter do we use to represent slope? M, right? So notice I'm asking how do we calculate slope, and you said rise over run. Let's work a little bit on that language. Rise divided by run. It's a ratio between the rise and the run, okay? One quick thing I will point out here, just because you may have seen this.
Please pardon the interruption, but the lockdown drill is now finished. It is now complete. Thank you.
So, other ways you may have seen this slope written in the past is the rise can be calculated as y2 minus y1 divided by x2 minus x1, which is also known as the change in y divided by the change in x. I focus on this one because it can always work, but you might have seen those two equations before. Have we seen those representations for slope?
Yes, sir.
Yeah. So they are connected. Notice if I find y2 minus y1, I am finding how much the rise is. If I do x2 minus x1, it gives me the run. I'm going to focus on that idea of rise divided by run now. Okay? As a graph, both of them have what kind of shape? Linear. It's literally called a linear function, right? Which means we're looking at a line. We all good with that information? Okay. And so again, you might have already had these details. If you do, you don't have to rewrite them. So this is you assessing, do you have this information or not? And if you don't, you need to write that down. So what are some differences? Actually, we already talked about the fact that an additive rate of change is called a common difference in a sequence. So if you remember, or actually let me say it this way, does anyone remember how we calculate a common difference? What would the common difference be here? Okay. A common difference, there's two different ways to understand it, but a common difference is only the difference between consecutive terms. Okay? So would the slope also be 4? Yes. But a common difference cannot help me find the stuff in between 5 and 6. Okay? A common difference, and what I mean by that is, let me clarify. A common difference does not help me actually get maybe what 5.5 is. Okay? A common difference is only associated with a discrete idea, a discrete function. Say again? Okay. So a common difference only goes with the idea of a discrete because we calculate it as whatever the current value is minus the previous. Right? Notice how that's f of n minus f of n minus 1. So it's the current output minus the previous output. What does this notation go with? What type of equation? Recursive, right? We want to recognize that this is recursive, which brings up the point, a recursive equation, should that go with the sequence or should that go with a linear function? That should go with the sequence, right? You can only have a recursive equation with a sequence. And we wrote this earlier. How do we write the equation for a sequence? For an arithmetic sequence?
Plus D.
That's where the idea of the common difference comes from. Right? So recursively we can say this. But I cannot put this idea with a linear function. Okay. Ooh, we forgot the most important difference.
What is that?
What is the big thing that separates an arithmetic sequence from linear functions? The arithmetic sequence, is it continuous or discrete?
Ooh.
So which one?
Discrete.
So remember, for a sequence, we would have something like, okay, the first term is 2, the second term is 5, the third term is 8. Notice how there's individual terms for a sequence? So with a sequence, it is going to be discrete. A linear function, which I will say, an arithmetic sequence is a type of linear function, okay? However, an arithmetic sequence is discrete. That's why we can use a recursive equation. So differences. Arithmetic sequence is discrete. Whereas a linear function, it's not necessarily that it is continuous. A linear function can be continuous. If a linear function can be continuous, can it also be discrete?
Yes.
Yeah. So that's a small difference. Remember, I said an arithmetic sequence is a type of linear function. So discrete sequences fall within linear functions, but a linear function can be continuous, and an arithmetic sequence cannot be continuous. Does that make sense?
Yes, it does.
We good with that idea?
All right.
So can I put this recursive equation over here under linear function? No.
Listen.
You can put an explicit equation here. Now I will say, can I put an explicit equation under arithmetic sequence?
Yeah.
Yeah, you can have explicit and recursive for arithmetic sequences. The big difference is we usually use an n for an arithmetic sequence. So remember, we start at the output. We're repeatedly adding the common difference n minus a times. And I'm just going to leave that there because you should have that already in your notes. In a different section, I would write it down here. But the equation for a linear function is typically this. Notice how additive rate of change is really my slope for a continuous function, but it's a common difference. Now, the common difference and the slope are the same, but we typically use m here. And then which variable do we usually use if it is continuous? X. Does anyone remember why we usually use n over here? Remember how we looked at the first term, the second term, the third term? 1, 2, and 3 are what type of numbers? Natural numbers, right? N goes with the idea of a natural number. Is anyone else cold besides Gavin? If so, I'll turn the air down.
Because I'm very cold, I just didn't want to complain.
You cold, Linnea? Okay. Alrighty. I think that is it for arithmetic sequences and linear functions. Let's look at geometric sequences. Actually, does anyone need me to leave this up here so you have time to write it down? Everyone who has what they want has it down? Okay. Alright, let's look at geometric sequences. So, geometric sequences and exponential functions both have multiplicative rates of change called what? They're called common ratios. Now, we'll say that is much like a common difference. Technically, it would only go under the geometric sequence, but I haven't really introduced the language for an exponential function I'm going to use right now. But what letter would we use for a common ratio? R. Really, the general term would be a constant factor, which we started to look at within lessons 2.4 to 2.7. That's where we started to look at that again. Okay? As a graph, both of these are going to have what kind of shape? It's going to have an exponential what? Curve to it. Does that mean every curve is exponential? No. So let's show an example. So I'm going to give a couple of different curves here.
That's exponential.
So which of these are exponential?
It's the first and third.
Raise your hand if you agree that it's the first and third.
I think it's the first, second, third, not the last one.
Okay, first, second, third, not the last one. Any other hypotheses? Alright, now we need to vote. So everyone should be voting. No one else has an idea, so we all either think it's 1, 2, or 3, or it's 1 and 3.
I
What I'm
think
hearing.
it's 1 and 2.
You think it's just 1 and 2? Okay. And then you think it's 1, 2, and 3? Okay. So raise your hand if you think it's 1, 2, and 3. 1, 2. Who thinks it's 1 and 3? 1, 2, 3. And then how many of us think it's 1 and 2? Those two. Cool. So, remember, if it is exponential, it has what kind of rate of change? Multiplicative, right? So if I look right here, let's just say that this is a 1. That'll be a 2, 3, 4. So notice that would be, that'd be roughly a half. Okay, so I see the point -1, 1/2, 0, 1, 1, 2, and 2, 4. And we all already said 1 looks exponential, right? Notice that pattern there? Okay? When I look at this one, might see something like this. Okay? So, -1, -1, 0, 0, 1, 1. What would I be multiplying by every time to go from -1 to 0 to 1? So -1 times 1 is 0, and then 0 times 1 is 1? Nope. Well, and it's not quite linear. If you actually look at the previous one to this, which we'll explore more later, it's -2, -8. 2, 8. I want you to look again. You see how this exponential curve is flattening out? And it's exponentially growing right here? Does this one flatten out? So is that an exponential curve? No. That exponential curve needs that flattened out portion and then it needs to shoot up. We all get with that idea? So this one does not have that idea. Personally, guys, I would actually draw all 4 of these sketches and show which ones are not and which ones are. But let's look here. It looks a little bit different than this one, so I understand why someone might be tempted to say no, but does this one flatten out? Yes. Does it start to shoot down instead of up? So this is a weird exponential, but this has transformations applied to it. What would have happened is it would have been vertically reflected and then translated up. That's why it looks the way it does. But it does have those features that we expect to see in an exponential curve. So yes, yes, and no.
Almost like I said.
I was impressed that Gavin got it, and proud of Alan and Jeffrey for recognizing that as well.
Well, I was-
Does that make sense though? What features we should be looking for in an exponential curve?
Yeah.
Okay? So, what are some differences that we should identify between geometric sequences and exponential functions? Probably look at some notes maybe we made under arithmetic sequences.
Exponential is continuous.
So an exponential function we think might be continuous, meaning a geometric sequence is discrete.
Yes.
Mona, what do you think about that assessment from Gavin?
Geometric being discrete.
He thinks geometric sequences are discrete, but exponential functions can be continuous.
No, we can, but I think it's continuous.
Which one's continuous?
Geometric.
Okay, why do you think a geometric sequence is continuous?
Hold on, let me get my thoughts back together.
Okay.
Yeah, freshwater shrimp.
And didn't you tell us not too long ago with continuous that, you're supposed to multiply?
No?
Um,
Why don't you go look at your notes of what you have for discrete versus continuous? I meant on the blue sheet. You should have already taken notes on there as well, earlier in the thing. While Mona's looking that up, Linnea, what do you think about Gavin's assessment that the exponential function can be continuous, but geometric sequence is discrete?
I agree.
You what?
I agree.
You agree? Why do you agree?
Because the sequence can't be continuous.
A sequence cannot be continuous. A sequence, you're saying, is always discrete? Okay. Alan, do you agree with them? All right, so raise your hand if you do agree with Gavin that the geometric sequence is discrete, but the exponential function can be continuous. I got 1, 2, 3, 4. Well, I assume Gavin agrees with Gavin. 4, 5, 6. Jeffrey, you're not sure? You are agreeing as well? So Mona, what do you think?
well, from what I'm reading here, I still kind of don't agree with that.
So let me point this out to you, Mona. Discrete versus continuous has nothing to do with the rate of change.
Okay.
Okay? Discrete means it's isolated points and it's not continuing between those points. Remember, continuous means that there's infinitely many points continuing between them. A sequence, though, and I think Linnea said this perfectly, a sequence is always those isolated points. Remember how under arithmetic sequence we just wrote that it was discrete, right? So a huge difference is a geometric sequence is discrete. Nope, that's a G, not a Q. We need to recognize that geometric sequences are discrete, just like arithmetic sequences. But remember, geometric sequences are a type of exponential function. So exponential functions are what? Actually, let me reword that. They can be what? There you
They can
go.
be continuous or discrete.
Good.
With my performance today, Mr. Kenny, I deserve those extra 2 points on my homework.
I'll consider it.
Yes.
Me too.
Yeah, okay, too.
I need the whole 5.
It's a package deal.
Well, I guess you both missing out.
Never mind, it's not a package.
How quickly he turns on you.
Well, look, it's either one of us might get something or both of us just aren't getting something.
Yeah.
Um,
If you don't, I'll jump with the window. It's very solo guy.
How about I make this deal with you?
Okay.
I got a deal.
Okay.
You score above an 80 on the quiz that all these homeworks are leading up to, I will replace every homework grade with an 80 or above or better.
This goes for just me or all of us?
All of us.
But what's the but?
There is no but.
It's being legit.
I'll pinky promise it.
No,
Just remind me.
shake my hand.
I didn't think this guy has a handshake.
Okay? So here's the thing. I'm sorry, okay, I can't leave you out. Here's the deal, right? Now please listen. The deal is, right, that I'm going to reward your understanding. If you forget to do homeworks, I get it. We have other stuff going on. However, I need you to understand, how likely is it that we score an 80 or better on assessments when we're not doing homework?
See, now we're just
It's a
gonna try
1 in
really
a
hard.
100.
It's what?
A 1 in 100.
100. I don't know if it's quite a 1 in 100, but that's what I need you to understand. The homework has never been to punish us. It's never been to make your life harder. It's to help you be better prepared for assessments. So I'm still going to be checking homeworks. I'm still going to be putting those grades into the grade book. However, if you manage to if you learn enough math to score above that 80, I will replace, I'll say it this way, I'll make all of your zeros an 80%.
Hey,
But this
I think
doesn't-
that's fair.
But this doesn't go for the homework today. My performance still deserves those 2 points.
No.
he's
I think this is a better deal.
Well, since Carol's not here, she don't get the deal.
No, everyone in class gets it.
No, she-
So when is the test?
I don't know yet. We need to finish 2.7 and then we're gonna have an understanding check on 2.7, and that's what I'm saying is the understanding check. So all the homeworks leading up to 2.7 will be replaced by a 4 out of 5 or an 80% if you score an 80 or better.
So we just don't have to do the rest of the homework?
No, don't do that.
No,
You're so trifling.
Imagine how much of a better grade you'd get if you do
Yeah,
those. And
that's my point. Well, my point is more that, I mean, you can try that, but the probability of you scoring an 80 or better without doing any of the homeworks is
Very low.
not very good.
It's
It's not just not guaranteed, it is not good. I am trying to give you an incentive to try to do better on the assessments, but also to give some leeway in understanding we don't always get all the homeworks done because we have other stuff going on. So I don't want you to give up on doing the homeworks, I just want you to know, hey, I'm gonna reward your understanding. Show me greater understanding, I will replace those homework grades.
Private discussion.
Now, while we're talking about homework, when you put what is homework, don't use what color you used yesterday. That was so hard to see on camera.
Okay,
For homework, please.
okay,
Thank you.
alright, I don't know, what?
It was like a teal green or something. It was so hard to see. Yeah.
Okay. So, we got our differences up here, right?
Sure.
Yes. Alright, equations. So what kind of equations can we use for a geometric sequence?
Recursive.
You can use a recursive, which would look like f of n equals f of n minus 1
Times R.
times r. And remember, we're just generically saying that the starting point is f of a equals b. So then, what would the explicit equation look like?
F of n equals f of n minus 1. I mean, never mind, I messed up. F of n equals b times r to the of a raised n minus a.
Okay.
You know the famous Rodney Carrington once said,
Okay, so now how does that change when we move over to an exponential function?
well,
Can we do a recursive for the exponential function? No. But you can still use the exponential to help you write the equation. F of what though?
f of x. Yeah.
Remember, for those continuous functions, we typically use an x, not an n. So f of x equals, we all good with this? Okay. Okay, so, oh, what were you still writing, Jeffrey? You got it? Okay. Arithmetic means versus geometric means. This is important because we struggled with this. What lessons can we look at for arithmetic means and geometric means? Do we remember?
1.2.
Not 1.2. It is 1. 1.9 for an arithmetic means. 1.10 for geometric means. You need to be clearly aware of this idea. Okay? What do the terms mean? That should say mean, not means. What do these terms mean? What do we mean by an arithmetic mean? Partially. So we do have arithmetic means when we are dealing with arithmetic sequences.
Linear.
Okay, so it would be the idea of linear. So what would it be for a geometric mean?
Multiplicative.
Multiplicative?
Yeah,
Notice
multiplicative.
that would be under the rates of change. I'm going to leave this alone for now because we're going to define this on the vocabulary graphic organizer in a second. But the rates of change, if it's an arithmetic mean, what's the rate of change? Additive rate of change, okay? Okay? And for geometric it is
Multiplicative.
multiplicative.
Gotta learn how to say it.
So what I want you to remember is there are specific strategies that help us identify these means. One thing I will point out, an arithmetic mean is honestly what we normally think of when we think of a mean. It is two numbers being added together, divided by 2. That is not necessarily the most efficient way to find an arithmetic mean, because that only gets you one mean. Sometimes we have lots of means to do. It is easier to write an equation to find the rate of change. Okay? It is easier to write an equation to find the rate of change. You all good with that?
Hold on. That's for arithmetic means, right?
Mm-hmm. I don't believe you.
I don't either.
But when it's a geometric mean, has a multiplicative rate of change, you'd actually have to take the square root of x1 times x2 to find that one mean. But again, that's not the most efficient.
Brett Favre is my cousin, I swear to God.
What?
I think you're a liar.
No, I can explain it.
What?
So, Papa's dad had a sister, a half-sister, and that half-sister slept with Brett Favre's dad.
Oh, God.
Please stop talking.
No, I'm serious.
Like,
Serious, I swear to God.
stop.
Please stop talking.
Fill me in.
His little,
No, Mona, stop being messy.
Noah Favre is his little brother, and his little brother is in jail for 7 years for shooting up a house.
Oh, dude.
How else would I know this?
Let
The news?
Google? Let's get back to this.
Good.
Never met the dude.
Are they dead?
No,
So,
don't think.
Okay, that's not.
man.
Let's stop.
What time is it?
story. It's time to learn in class.
Yeah, why you gotta be at work like 12 minutes?
So we'll have to finish up these notes tomorrow, which means, guys, we've got to get faster at having discussions and learning and talking.
It's fault.
Do not do the question on the back for homework. Just do the 3 circled problems on this sheet for homework, and I will assign others tomorrow. Ooh, don't do number 15 then, let's do number 14. So 12, 14, 16, do those 2 tonight. Please note, this is just going to be a check to see that you do it now. It will be a check for accuracy tomorrow night, is that clear?
Yes, sir.
Okay, use your graphic organizer to help you as much as possible. Do note that I am telling you which lessons to look at to help you figure out these different things. Use your notes, use your homework, and if at the very least, if nothing else, what resources do you have online that can help you?
Symbol Lab, Khan Academy, and other things.
And
Khan Academy. Okay, so Symbol Lab, Desmos, Khan Academy. If you don't have a computer at home, you can download apps for all 3 of those,
Mr.
okay?
Kenny?
Yes, ma'am.
Why don't I have a grade on here?
Yes, I know she.
Man, it was a homework check. You
That's
graded
the
it.
homework. Oh, that's
Oh,
that.
okay.
So we'll get to all that tomorrow.
Oh, that's the.
So we changed this to be 12, 14, and 16. You have a few minutes left in class. I can go ahead and start on them instead of just sitting there wasting time. You can ask me questions while you have time.
Can we just have a conversation?
Oh, I guess to be fair, I will admit, we had 10 minutes wasted for us. We would have gotten further along without the,
See, I said that. Probably didn't hear me.
I did not hear you, that's my bad.
Yeah.
I agree with you on that.
On which book?